Any advanced microprocessor-based relays, such as the URD60, gives the user the ability to further customize the shape of the MO circle to meet their protection needs. For example, if this power system has instances where it can be heavily loaded, which may cause the impedance of the line to encroach into the MO circle, the area of the circle may need to be changed to not include this area in the zone of protection. The MO zone can be altered to form a lenticular shape, which looks at the magnitude of the impedance and only allows tripping when the impedance falls very close to the angle of the transmission line impedance. Therefore, highly loaded systems which cause the impedance point to approach very near the origin will not result in tripping the transmission line. As a side note, the D60 relay also gives the protection engineer the ability to configure the MO characteristic into what is known as a tomato-shaped zone. A tomato-shaped MO characteristic allows for faults that have more of a resistive element to fall into its zone of protection. Another custom zone is known as a quadrilateral zone of protection. This type of zone allows you to set the reactance and resistive upper and lower boundaries to create your own custom shape to match the needs of your power system. In this type of zone, there are essentially two reaches, one in the inductive direction and one in the resistive direction. Some advanced distance relays have added features to the MO circle characteristic to increase security and reliability for faults that occur very close to the point of measurement, which is at the beginning of the transmission line. Again, this point of measurement is shown at the origin of the RX diagram. On faults that occur very close to the point where the currents and voltages are being measured, some relays may have difficulty distinguishing whether the fault is inside or outside their zone of protection. To overcome this difficulty, the relay can change the size of the MO circle when the calculated impedance is very near the origin. This is sometimes referred to as an enhanced MO element. If a fault occurs just before the beginning of the transmission line, and the transmission line is double-ended or multi-ended, current will flow into the CT from the opposite direction. If the relay now calculates the impedance of the line, the value will be negative, and plotting that impedance point will put it very near the origin, but in the reverse direction to the transmission line. To make sure that the MO characteristic does not mistake this as being an internal fault, the relay recognizes the low impedance of the line, sees that the value is negative, and shrinks the radius of the circle. Since the MO circle is no longer near the origin and the location of the fault, there is no chance of the relay false tripping. Notice, however, that the reach of the MO circle did not change and still extends out to the end of the original zone of protection. If a fault occurs just after the beginning of the transmission line, current will flow into the CT from the positive direction. If the relay calculates the impedance of the line, the value will now be positive. Plotting that impedance point will put it very near the origin in the positive direction of the transmission line. To make sure that the MO characteristic does realize this as being an internal fault that needs to be cleared, the relay recognizes the low impedance of the line, sees that the value is positive, and enlarges the radius of the circle. Since the MO circle now extends past the origin to include a larger area, the location of the fault is sure to fit in the zone of protection. Therefore, the fault can be cleared properly. Notice, however, that the reach of the MO circle did not change and still extends out to the end of the original zone of protection.